Okay, let's dive right into this explainer. Today, we're going to take something totally mundane, something you've probably seen 1,000 times, and reframe it into an absolute cosmic anomaly. I'm talking about fire. It's so deeply baked into our human experience, right? It sparked civilization, cooked our food, kept us warm, and let us forge metals. But honestly, beyond just striking a match or turning on a stove, have you ever stopped to think about what is actually happening inside those flickering flames? Because it is literally one of the most fascinating processes in the natural world. Think about the last time you were just chilling around a campfire. As you stared into those twisting, dancing shapes, you were feeling the heat, smelling that woody smoke, and listening to that awesome crackle. But if you had to categorize exactly what you were looking at right there on a fundamental level, where does it fit? I mean, it's definitely not a solid, and it's clearly not a liquid. It kind of mingles with the air, so you might think it's a gas. But unlike the air around us, you can see it plain as day. It's almost like, I don't know, painted air, where the heated air currents are the canvas and tiny glowing particles are the paint. So where exactly does it belong? Well, the answer might actually surprise you. It's none of the above. Turns out, fire isn't actually a state of matter at all. Think about it. Gases can just exist in the same state indefinitely, but a fire? It always eventually burns out. It's fleeting, it's temporary, and it's completely unclassifiable as a physical object.
Now, a really common misconception is that fire is a plasma. We hear that plasma is the fourth state of matter, and since fire actually bends when exposed to a strong electric field, people just assume it fits the bill. But actually, scratch that. True plasma only forms when gases are superheated to thousands or tens of thousands of degrees, which literally strips the atoms of their electrons. And typical fuels in a campfire, like wood or paper, they burn at just a few hundred degrees. That is way, way below that extreme temperature threshold. So if it's not a solid, not a liquid, not a gas, and not a plasma, what on earth is it?
It's combustion. What we call fire is really just our vivid sensory experience of a super rapid chemical reaction taking place right in front of us. In a weird way, watching a fire is exactly like watching leaves change color in the fall, or seeing a firefly blink in the dark, or even smelling a piece of fruit as it ripens. It is just a highly engaging visual clue that molecules are actively rearranging themselves and releasing heat and light while they do it. It engages so many of our senses all at once that our brains trick us into thinking it's a physical thing, but it's really just the visual ghost of a chemical event. Let's move to section 1, the fire tetrahedron and a push down the hill. So, to make this visual ghost appear, we need 4 specific ingredients, which together make up what is known as the fire tetrahedron. First up, we need fuel, basically anything that can burn. Second, oxygen, which is the ultimate oxidizer. Third, heat, just to get that fuel up to its ignition point. But the fourth and absolutely crucial step is a rapid chain reaction. This oxidation, the stealing and swapping of electrons between the fuel and oxygen, has to happen so fast that the heat being generated can't dissipate faster than it builds up. Knock out literally any one of these 4 pillars, boom, the flame completely vanishes. This whole underlying reaction happens because the universe has this intrinsic preference, really, for things to be in their lowest, most stable energy state. Imagine a ball just sitting at the top of a steep hill. It's stable for the moment, sure, but it's packed with potential energy. Now, if you give that ball a little push, in this case, spark it with some heat, it's going to seize that opportunity to roll right down that symbolic hill. In chemistry, fire occurs because the resulting products, stuff like carbon dioxide and water, are just way more chemically stable than the initial fuel and oxygen. All right, section 2, the quantum chemistry of combustion. To really wrap our heads around this, let's think of the periodic table as a series of concerts. The further to the right you look, the better the concert. Fluorine? Fluorine is throwing the absolute best, most exclusive concert of the decade. It's the most electronegative element, meaning electrons desperately want to get in. But fluorine only has one open seat, and once an electron grabs it, it never leaves. Oxygen, on the other hand, is throwing the second best concert in town. And here's the kicker. It has 2 open, highly desirable front row seats. Because oxygen is super electronegative and incredibly abundant in our atmosphere, it's constantly roaming around trying to yank electrons away from other elements to fill those seats. That is exactly why oxygen is the ultimate driver of fire on Earth. But hold on, oxygen can't just walk up to a solid log of wood and rip those electrons out. There's a really crucial intermediary step that has to happen first. It's called pyrolysis. The heat of the fire actually vaporizes the solid fuel, literally tearing those complex molecules into smaller gaseous chunks. You simply cannot have a flame without pyrolysis. When you're sitting by that campfire and you hear that super satisfying hissing or cracking sound, that is actually trapped water expanding and the solid wood chemically decomposing into a gas. It's that escaping gas that's catching fire, not the solid log itself. How crazy is that?
Let's tie this all together with a really simple example: combusting methane. You add heat, and the methane and oxygen molecules start vibrating so intensely that their chemical bonds just snap apart. Suddenly, all these electrons are totally free, and they immediately rush the stage to grab those prime concert seats that oxygen is offering. As they rearrange into those highly stable carbon dioxide and water molecules, they drop into a lower energy state. And just like our ball rolling down the hill, they have to shed their excess energy. That energy blasts outward as intense heat and the visible light that we see as a glowing flame.
Section 3. Anatomy of a flame. Let's look at why they actually look the way they do. You know, if you look closely at the colors of a flame, they're actually telling you a story about exactly what kind of fuel is burning. Burn a large complex molecule like wood or candle wax, and the reaction is kind of messy and incomplete. Not all the carbon atoms manage to react with the oxygen. So, those leftover unburned carbon atoms clump together and form tiny particles of soot. The intense heat makes that soot glow a bright yellow and orange through a process known as black body radiation. Literally the exact same reason an iron rod glows in a blacksmith's forge. But if you burn a really simple gas, like methane on an efficient kitchen stove, you get complete combustion. No soot left behind at all. Instead, you get this super clean blue flame. And that blue light isn't glowing soot. It's the specific emission spectrum of the chemical radicals releasing energy right as they form.
And what about that iconic teardrop shape? Well, that is entirely thanks to Earth's gravity. As the fire heats up the air around it, that hot air becomes less dense and shoots upwards. Meanwhile, gravity pulls the cooler, denser air down to rush in underneath. This creates a convection current, basically a localized mini wind that pushes the glowing soot up into a point while constantly feeding fresh oxygen in from the bottom. But get this, if you light a flame in zero gravity, like up on the International Space Station, there's no up or down for the air to flow. Without gravity driving those convection currents, the flame just slowly expands outward into this bizarre, perfect spherical dome. It burns way slower, just waiting for oxygen molecules to lazily diffuse into it.
Section 4. The rarest cosmic phenomenon. Okay, here is where things get truly mind-blowing. The crucial point is this: fire, as we know it, is incredibly, almost impossibly rare. In fact, we have never found fire anywhere else in the universe, except right here on our little blue dot. Now, I know what you're thinking. What about the sun? What about a fiery volcano? Well, despite the words we use, the sun is not actually burning. There is zero oxygen there. The sun is powered by nuclear fusion. It's just violently crushing hydrogen atoms together. And those glowing rivers of lava from a volcano, that's just molten rock radiating heat through thermal black body radiation again. Neither of those involves the chemical combustion of oxygen and fuel. Cosmic fires are a total myth.
And the crazy thing is, the universe is absolutely packed with fuel. Just look at Saturn's moon Titan, for example. That place is covered in massive, sloshing, liquid oceans of methane. Methane is an incredibly potent fuel, but there is absolutely zero fire on Titan. Why? Because it's missing the oxygen to complete our fire tetrahedron. You could literally toss a lit match into Titan's oceans and nothing. It would just fizzle right out. Without oxygen there to pull those electrons down the energy hill, that massive ocean of fuel just sits there completely inert.
Which brings us right back home to Earth. If you possessed a time machine and traveled back to the early days of our own planet, you'd find a big fat zero when it comes to oxygen in the atmosphere, meaning there was absolutely no fire here either. It wasn't until a tiny microscopic organism called cyanobacteria evolved the neat little trick of photosynthesis that oxygen slowly, finally began to fill our skies. And that leads us to a pretty profound realization. Because all the oxygen in our atmosphere was completely manufactured by living organisms, and because almost all the fuel we burn, from a block of wood to ancient fossil fuels, stems from organic life capturing the sun's energy, fire is inextricably linked to biology. Fire requires oxygen requires life. Therefore, every single time you strike a match, light a candle, or just stare into the dancing painted air of a campfire, you aren't just looking at a chemical reaction. You are witnessing a phenomenally rare cosmic anomaly and a brilliant, glowing footprint of life itself. So it really makes you wonder, what other incredibly mundane things around us are hiding such a profound cosmic secret? Definitely something to chew on the next time you're sitting around the fire.